Hey guys, my name is Gaurav and I'm going to talk about collisions. It is a very widely used phenomenon and a very widely seen event around us. Simply put, is nothing but the meeting of two or more objects with a significant amount of force. Now, you giving a high five to your friend is a collision. You watching a car crashing into a wall or another car is a collision. You kicking a football is a collision. You hitting a ball with a bat is a collision. And you watching a plane crashing into the building and collapsing the entire building is a kind of collision. Oh, I wasn't really supposed to talk about that. Anyways, cut. So, yeah, let's see the physics of collisions. Before I talk about the physics of collisions, I'm going to take a very and that assumption is that you know what is conservation of momentum and you know what is conservation of energy. In case you do not know, I'll give you a quick recall. Law of conservation of momentum. Now, when is momentum conserved? If we recall from our Newton's second law, we'll say we define force as rate of change of momentum. And in case if your external force is 0, your rate of change of momentum has to become 0, which simply says that your initial momentum becomes equals to final momentum in case F external is 0, right? And the second theorem was conservation of energy, law of conservation of energy. Now, it simply says that the total energy of a system remains constant. Now, when does it remain constant? It has a few conditions for it. And those conditions are that the work done by external forces should be equal to 0 and there should not be any non-conservative forces involved. No non-conservative forces involved. Now, I begin my story talking about two blocks. And I would want you to notice what happens to the energies and the momenta of these blocks before the collisions, at the time of the collisions, and after the collision. So let's just take two blocks, right? Let us call this block as block A. Let's call this block as block B, right? And I'm going to make a small modification into block B, and I'm going to attach a small spring to block B. And the spring is massless spring and it has a spring constant K. Okay, just for the sake of a better understanding, I'm doing this modification. You will realize its worth in the subsequent derivation. And let us say their initial velocities are v1 and v2. And just assume that v1 is greater than v2. This is the first chapter of my story. Now, in this first chapter of the story, block A is following block B with a greater amount of speed. There is no friction involved, and all the forces acting will be the conservative forces, if and all they act. Now, at this instant, I want you to write down two steps. First step, I want you to write down the net momentum, which would be simply m1 v1 plus m2 v2. I'm really sorry, name this as m1 and call this as m2. And at the same instant, I would want you to write the net energy of the system. Now, the net energy of the system is nothing but the kinetic energy possessed by both these objects, simply half m1 v1 square plus half m2 v2 square. And this is our instant 1. Instant 1, just call it, this is t equals to 0. This is the beginning of our story when object A follows object B. Let us talk about instant 2, call it at t equals to t1. Now, at t equals 0, I saw that the velocity of the object A was greater than the velocity of the object B, which means it could be very well assumed that object A at some instant is going to meet object B. Let us decide this as our meeting point. This is object A meeting object B. When the object A is meeting object B, it is compressing the spring by some amount, right? I have taken a photograph of that instant when the object A's velocity is decreasing. Object A ka velocity is decreasing and object B ka velocity will start to increase. But let's just not conclude these things, and let's just say that the velocity of object A is v1 dash at a distance and velocity of object B is v2 dash at this instance. Again, I would want you to write down those two important things. Those two important things are net momentum. So what is net momentum? Net momentum is again m1 v1 dash plus m2 v2 dash. And again, I would want you to write down the net energy of the system. The net energy of the system is the kinetic energy possessed by both the objects. But also do not forget that the spring has been compressed by some amount, which means the spring will also acquire some amount of potential energy. So net energy is half m1 v1 dash square plus half m2 v2 dash square plus half k x square. Nice. Not much fun happening till now. Let us look at instant 3. This is where they meet and this is where they fall in love. And you decide for yourself. This is my instant 3 when the compression in the spring is maximum and the heartbeats are at the highest rate. Block A, block B. The compression is maximum. Call this maximum compression to be sum of some value x naught. Right? Again, at this instant, what I would want you to write down is the net momentum. And then again, I would want you to write down net energy. Now, at this instant, first of all, visualize this is the instant when the spring has been compressed by the maximum amount. The spring has been compressed maximum. The spring cannot compress anymore. The spring at this instant is not even decompressing, which means the two ends of the spring do not move relative to each other, which means the block A and B have to go at the same speed at this instant. So what would be my net momentum? Net momentum will be m1 plus m2 to v, and the net energy will be half m1 plus m2 taken common v square plus, because the spring has been compressed by maximum amount, so it is your maximum potential energy. All cool and fine till now. Let us talk about the instant 4, and the instant 4 will be our deciding thing, how your love story ends. Now at this instant, the blocks are separated. Don't be sad. Blocks are separated. This is again your block A, block B, and I just wanted to give you a clue, or just think whose velocity will be more. Now, when the spring was compressed by maximum amount, when the spring started decompressing, the spring applied. So okay, I'll draw it here. The spring applied a force, some amount of force to block A1 in the backward direction, and the same spring applied force to block B in the forward direction, which means this block A will be deaccelerated and block B will be accelerated, which means the velocity of B is going to be more than velocity of A. That too, if it comes to you intuitively, really nice. If it does not, please do not bother. Your mathematics will give you all the answers. So let us call this velocity to be v2 double dash, and let us call this velocity to be v1 double dash. Again, at this instant, I will write the total energy and the net momentum. So net momentum is nothing but again m1 v1 double dash plus m2 v2 double dash, and the net energy after departing is half m1 v1 double dash square plus half m2 v2 double dash square. So this is the end of my observations, and this is where I should start making some conclusions. So the first conclusion that I make is the total energy of the systems at all the instances will remain same, and the total moment of at all the instances will remain same. Why? Because in the beginning itself I established that there are no external forces involved, there are no non-conservative forces involved, which means momentum at first instant will be equal to momentum at second instant, which will be momenta at the further instances, and similarly total energy at first instant will be equal to total energy at second instant will be equal to total energy at third instant, and same as is going to be total energy as fourth instant. When you say total energy 1 is equals to total energy 4, involved half m1 v1 square plus half m2 v2 square, this should be equals to half, then when I say total energy 4, half m1 v1 double dash square plus half m2 v2 double dash ka square. Now this is something really interesting when you see that the total energy initially is nothing but the total kinetic energy, and total energy finally is nothing but the total kinetic energy, which means there is no spring potential energy. This, dear friends, is the case of elastic collisions. Now, how do I establish this thing? I took a very daring assumption, and this assumption misses a lot of people's eyes. The assumption was in instant 3 I had some significant amount of spring potential energy, and instant 4 I did not have any significant amount. In fact, there was zero amount of spring potential energy, which means my assumption was that the spring was completely elastic. The spring was fully elastic, which implies that the total potential energy accessed by the spring goes back to the system in the form of kinetic energy, and this type of collision is known as elastic collision. But this might happen and this might just not happen. In our day-to-day life collisions, this will usually not happen. The total potential energy acquired by the spring, or the total potential energy acquired by any system, just imagine two cars crashing into each other. When you separate those cars, the dent does not come out immediately, which means the energy, some amount of energy has been consumed in the making of the dent. Sorry, the total energy in instant 4 would be generally written as half m1 some v naught square plus half m2 some v naught dash square. I don't really care what v naught is, but then you also add some amount of potential energy, because I do not know that the spring has been, whether the spring has been fully compressed or fully decompressed. This part is usually the loss in energy, right? But again, you will still say that the total energy initially is equals to total energy finally. But you cannot say that the kinetic energy initially is equals to kinetic energy finally. When this case appears, when this is the case, when some amount of energy remains in the form of potential energy, or this energy can also be counted as the loss in the form of thermal energy or the sound energy or the light energy. This happens. When this happens, this kind of collision is termed as inelastic collisions. And now I would very smartly conclude what is a completely elastic collision. Let us completely non-elastic collision. Let us revisit our step 3. Now, for it to be completely inelastic collision, your spring should be perfectly inelastic. When you say that the spring is perfectly inelastic, no amount of spring should again decompress. When this happens, if the spring does not decompress, when this happens, both the blocks continue to move with the same speed. So when instant 3 continues as instant 4, this collision will be termed as completely perfectly inelastic collisions. And as you can see, in perfectly inelastic collisions, still your total energy is conserved, but you see both the blocks always move with the same velocity. So let us conclude our discussion by making a few takes. We know that the total energy, we just realized and we just said it multiple times, that the total energy of the system remains conserved whatever the case may be, but the kinetic energy remains conserved only in the case of elastic collision. It is not conserved in the case of inelastic collisions, and momentum, whatever the case may be, is always conserved because there is no net external force involved. Also, a lot of viewers might feel that why am I attaching a spring to a block? Usually you will not see objects wearing springs because we still live in a sane world. The spring only depicts the elasticity of an object. I could have simply done this entire story with two spheres colliding, but I wanted to show this collision time when the spheres get compressed by some amount. I wanted to show this compression time and the decompression time minutely, and that is why I took the spring. Spring simply depicts the elasticity of the objects, nothing else. So when I say spring potential energy is half kx square, it's nothing but the elastic potential energy stored by the objects. I hope you enjoyed this topic. Thanks a lot.